Alright, let's get going here today, please. You had several questions waiting for you on the Socrative app today. And the first of these, actually about the first three or four, pertain to the question we ended with a week ago today, and that is we had written up on the board or on the screen somehow to write an equation that shows the complete combustion of octane. So if we start off with this and look at the answers, the correct answers for the products here would be CO2 and H2O. And remember, when we burn something, if it contains carbon, one product of that reaction is going to be carbon dioxide. And if it contains hydrogen, one product is going to be H2O. Any questions on this one here? All right, next up. When writing a balanced chemical equation for the complete combustion of octane, the smallest whole number coefficient of the O2 is, correct answer for this one is 25. Looks like we need to go through this one. Next up. When we write out an equation for the complete combustion of octane, with the smallest whole number coefficients, the coefficient of CO2 is 16. The coefficient of the H2O is 18. And then, of course, if we look at the last one here, when this equation is balanced using the smallest whole number coefficients, the coefficient of the NH3 is, correct answer on this one is 4. So it does look like we need to go through this one, and let's do that here very quickly. We'll start by looking at remembering our strategies, and we talk about the complete combustion once again. We talk about the complete combustion of O2. That means that, or not of O2, but of octane. We burn this in the presence of oxygen. Because it contains carbon, one product is going to be carbon dioxide. Because it contains hydrogen, one product is going to be H2O. Then, in order to balance this, we look at our strategies. Our strategies tell us that we are going to balance the simplest formula or element last. And all of these, which one is the simplest formula? O2. So we're going to balance the O2 last. So that means we start with the carbon. Over here we have how many carbon atoms? 8. Over here, how many? 1. So in order to balance it, what do we put in front of the CO2? 8. If we go then to the hydrogen, how many hydrogens on the left? 18. On the right we have 2. What number do we have to put in front of here to get 18? Put in a 9. So that balances the hydrogens. We've done our job now. Our job was to balance everything except for the oxygen, and that's all we have left. So how many oxygens do we have here on the left? 2. How many do we have on the right? 25. We have 16 here plus 9 here. So again, we have 16 plus 9. On this side we have 2. That means we should be able to put some coefficient in front of this in order to balance this chemical equation. If this was an algebra class, we wouldn't call it question mark, we would call it x, or some other variable. So basically that's telling us 2 times x is equal to 16 plus 9. If we take 16 plus 9 and add them together, we're going to get 25. If we now want to solve for x, we would have to divide each side by 2. If we divide each side by 2, we find out that x is equal to 25 halves. We place the 25 halves in here. Of course now, we can't leave this equation as is. If we use fractions to balance it, then we need to multiply it through by an integer that removes the fractions. Which integer do we need to multiply this by? If we multiply it by 2, we then distribute over the quantity in parentheses. 2 times 1, of course, is 2. 2 times 25 halves is 25. 2 times 8 is 16, and 2 times 9 gives us 18. This then is your balanced chemical equation. What one should do once we get this is check to make sure that this balancing is correct. How many carbons are there here? 16. Over here we have 16. How many hydrogens here? 36. 18 times 2 is 36. How many oxygens here? 50. Right here we have 32 plus 18. 32 plus 18 gives us 50. This is about as hard as they will come on your exam. I know somebody had placed a question up on the discussion boards about another one that was even more difficult. That even more difficult is not going to be one that could be on the exam, but this is definitely one that is fair game for the exam. So any questions on this one? Okay, then our next one, we have N2H4 breaking down to yield NH3 plus N2. If we were to balance this, the simplest formula is going to be which one? N2. So that means we'll balance the nitrogens last. If we're going to balance the nitrogen last, that means we balance the hydrogen. So if we balance the hydrogen, how many on this side? 4. On this side we have 3. We follow our strategies. Best strategy for this one is to use the least common multiple. Least common multiple between 3 and 4 is 12. In order to get 12 hydrogens on the left-hand side, we'd put in a 3 out front. To get 12 hydrogens on the right, we'd put in a 4. That would balance the hydrogens. And we look at the nitrogens. How many nitrogens here? 6. How many here? 4 plus 2. That gives us 6. This here is a balanced chemical equation. Any questions on either of these two? All right, we'll do a demo here and take a look at what may happen with this one. With this particular one, I have a liquid, it's not a solution, but some pure methanol. What I'm going to do here is I'm going to place this methanol into this 2-liter bottle. And we'll go ahead and set this methanol aside. Then we're going to go ahead and shake this up a bit and see what happens with this. This, of course, is more exciting if we turn the lights down a bit. So we'll turn the lights down. And oh yeah, you know, probably should get something else out here. Hang on. Haven't used this for a while. Get the explosion screen out. And if you startle easily, you may want to cover your ears for this. And it's not that I expect that there's going to be any sort of explosion. It's just that I put it up here just in case there could be one. And we'll go ahead and light the wood splint. There we go. We'll bring it over to this and we'll watch to see what happens. There we go. And then of course we see the reaction that takes place. Now, one of the things I can do with this is I can go ahead and rinse this down the drain, and we can go ahead and try this again. I used to actually do this with a large carboy, and Unfortunately, this has been a demonstration that they recommend we no longer do with the large carboys. And I do have the explosion screen up there for that reason. But again, we'll go ahead and shake this up a bit. And we'll go ahead and put this up here. And we will go ahead and light the splint again. And we'll watch what happens when we do this. Again, if you startle easily, you might want to cover your ears. And now if you watch this one, if you notice what happens to the splint when I put it in here. In fact, the only place that this one is burning is, I don't know if you can even see it, is where? Yeah, and I think it's not even burning up there anymore. I can put my hand over the top of this, and there's a very good reason why it's not burning up there, or burning only up here and not anywhere inside. And what would be the reason why we did not see the whoosh the second time? Any ideas? Well, let's see. The substance we're looking at, you didn't see its formula before, but let's go ahead and look at that right now. The substance we're looking at is methanol, which is CH3OH. If we wrote out a chemical equation that showed the complete combustion of methanol, what would the products of this reaction be? What would the products of this reaction be if we did the complete combustion of methanol? Carbon dioxide and H2O. It's not a mystery because, again, the methanol contains carbon, so if we burn it in the presence of oxygen, it's going to produce CO2. And because it contains hydrogen, the other product is going to be water, or H2O. So the first time I ignited it, of course, we saw the whoosh because it contains some oxygen on the inside. And so that oxygen and the methanol wound up burning off. When I tried to burn it the second time, what is now inside of this bottle? H2O and carbon dioxide. And what does carbon dioxide do to flames? Puts them out. Okay, so I don't know if you've done that lab yet. Have you done the lab with the where you generate some carbon dioxide gas or hydrogen gas? No. Oxygen? You haven't done that one? Okay, so you'll be doing that one at some point. But one of the properties of oxygen is that it would reignite a glowing splint. And one of the properties of carbon dioxide is it puts out fire. And in fact, if you walk through this building here and look at some of the fire extinguishers, you'll see that fire extinguishers, except for in the chemistry lab, the fire extinguishers that we have around the campus contain carbon dioxide. And so we use them to fight fires. All right, so write out an equation that shows the complete combustion of methanol. This is our last of the combustion reactions. I'll give you about, probably about 2-3 minutes. Write out an equation that shows the complete combustion of methanol. And the first question then on the Socrative app here for our lesson today would be to write down what that coefficient is on the O2. If you came in late, who needs a copy of the handout for today? Anybody else need a handout? You'll need to use probably all 3 or all 4 strategies. Remember to say the simplest formula to last. How many have it balanced and are confident they have it balanced correctly? Raise your hands. Okay, look to those that have their hands very confidently raised, and if you don't have it, turn to one of them to get some help. Right now, if you don't know how to do it, get some help. I'll give you 1 minute to get your help. Okay, let's check out the answer on the Socrative app. We'll count down on this one. 5, 4, 3, 2, 1. Correct answer here is 3. To arrive at your answer, here's how we might go about doing this. First of all, which element do we save to last? O2. So then we go to the carbon. How many carbons on the left? 1. How many on the right? 1. How many hydrogens are on the left? 4. How many on the right? 2. So what do we need to put in front of the H2O? Put a 2 over there. Good. That balances it. That means that the only element left to balance is the oxygen. If we want to balance the oxygen, we can look at this one right here. Oh, let's see how many oxygens we have on the left. How many oxygens in this formula? 1. How many oxygens in this formula? 2. How many in this one? 2. And how many here? 2. So these are the number of oxygens. Now, because we saved oxygen to last, it means we should be able to put some number here in front of the O2 in order to balance it. Of course, if this was algebra, we wouldn't put in a question mark. We'd put in x. So we could say that this is x. So this is basically what this algebraic equation is going to look like. At this point, we take this equation and solve for x. That means we're going to subtract 1 from each side. If we subtract 1 from each side, we wind up with 2x is equal to 3. In order to solve for x, we divide each side by 2. Divide each side by 2, we find out that x is equal to 3/2. We put in the 3/2 right here. Of course, we can't leave it with a fraction, so we have to take this entire equation, multiply it by a factor of 2. We distribute the 2 across parentheses. We get a 2 here. 2 times 3/2 is going to equal 3. 2 times 1 will equal 2. And 2 times 2 will equal 4. And this then would be the balanced chemical equation. Again, this is about as difficult as they will come on your exam. Any questions? Any questions? All right. Quick reminder here, we do have an exam coming up next Tuesday in here. The exam will begin at 8 o'clock. It'll be alphabetical by last name, A to Z. We did have one special seating request last time. Rather than me passing out again, if you do have a special seating request, do talk to me here after class, and I will set you up for your special seating request. Assuming that it's the same, this is the first time ever between exam 1 and 2, we've had 0 people drop the course. So you should be in the same seat as you were last time, and so wherever you were, unless I get another special seating request, you'll be in the same spot. The exam will cover chapters 5 through 7. We will, on the exam, be supplied, not with strategies, but we will be supplied with this solubility table that we'll be going through next. But what you can expect besides being supplied the solubility table, chapter 5 is all about nomenclature. We had a nomenclature worksheet that we passed out in here. The nomenclature portion of that exam will look almost identical to that worksheet. That is, there'll be some for which you'll see names, you'll need to write formulas. If you see formulas, you'll need to write names. There'll be some of them where you might be asked, like we learned about what is sulfate, but then you need to know the formula of sulfite. There'll be a few others besides that, but the majority of the nomenclature stuff is going to look like that worksheet we had passed out in here. That is going to be worth about 1/3 of the exam. Historically, this is like an all or nothing proposal for students. I either see perfect scores or near perfect scores, or I see almost zeros on that. Of course, the side you want to be on is the almost perfect, right? And the only way you get almost perfect is by practicing and studying. And this is the type of stuff that you go back to when you were in elementary school and you saw multiplication tables over and over and over again every year. The nomenclature is going to be the same thing. If you think you have it, you don't have it. You probably are going to do very poorly on it. You have to know you have it in order to succeed on this. So I would go back to practice nomenclature over and over and over until you get that down. Chapter 6 was on the mole concept. So we did things like converting grams to moles, and moles to grams, and grams to molecules, blah, 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 with the topic of this number. This is going to be a portion of the exam that's going to use a bunch of conversions. And then you need to know your terms, the distinction between molar mass, molecular mass, atomic mass, formula mass, and such. We introduced the concept of formula units. We looked at mass percent composition and stuff like that. And then chapter 7, we are working on chemical equations. Last class we worked primarily in balancing chemical equations and then taking word equations or word descriptions and writing out equations from those. So you're going to see that. And then we ended the hour on Tuesday last week by looking at completing and balancing combustion reactions. Today we're going to be working on completing and balancing double displacement reactions. and that will be part of your exam. So any questions on your expectations? Going once? Twice? There will be less multiple choice on this exam, more open answer, just as an FYI. So like the completing and balancing, the balancing, and stuff like that. All right, so let's have this out. Again, on your exam, you are going to be supplied with a list of solubility rules. It will look just like this. You'll be provided with this to use on your exam. So we're going to start here by looking at double displacement reactions. And remember that double displacement may also be called double replacement reactions. In fact, most chemists use the term double replacement, but double displacement is a term that is used by your author. Now, in double displacement reactions, it looks something like this. We have a couple substances, which we'll label as AB, and another that we'll label as CD. These represent formulas of ionic compounds. When these react together, what happens is that the positive ions trade places. The positively charged ions trade places. So if the positively charged ions trade places, what would the formulas of the products be? AD and what else? CB. Right, so if the positive ions trade places, products are going to be AD and CB. So let's look at an example where this would take place. I'm going to take two substances. These two substances are calcium chloride. We might as well write out their names right now. Calcium chloride. And the other substance here is sodium carbonate. And to kind of help you out with this, when you write these out, write the names one above the other. So it's going to be calcium chloride, and the other product is, or the other reactant is, sodium carbonate. We'll take these two and mix them together and watch what happens when we do it. I think we may have even seen this one before, putting the two together. What do we call this when we form it? Precipitate. We describe it as a white precipitate. So we mix the two together and we observe the formation of a white precipitate. So now we want to write out a chemical equation that shows what happens. First of all, we're going to write out formulas for the two reactants. Let's write out a formula first for calcium chloride. If we're going to write it for calcium chloride, it might be helpful to get out our periodic table. And I believe I have a few more here. Anybody needs one? Anybody need a fresh, clean copy of the periodic table? Remember, you can never have too many. See? Can't decide. Somebody else needs one. All right. So now we want to write a formula for calcium chloride. Calcium, right here on the periodic table. Calcium has a charge of 2+. Chloride is Cl with a charge of 1-. So if we have calcium, which is Ca with a 2+ charge, chloride, which is Cl with a single negative charge, formula for calcium chloride is going to be CaCl2. If we look at how we started with this, the phase label for this is going to be AQ. It's going to be AQ. One of the few liquids we're going to work with in here is water. If we see an ionic compound and it appears as if it's a liquid, that means it's been dissolved in water. So again, this here is calcium chloride. This is an aqueous solution of calcium chloride. We put in a phase label of AQ. Then for sodium carbonate, sodium is Na with a charge of 1 plus. And carbonate, we now see an ATE suffix, which tells us which element is there for sure. Oxygen. So this is one of your polyatomic ions. Formula for the carbonate ion is CO3 with the charge of 2 minus. You need to have these memorized. So then if we write out the chemical formula for sodium carbonate would be Na2CO3. It appears to come as a liquid, but it's an ionic compound, so we'd write a phase label as AQ, as aqueous. So again, these are our 2 reactants. Once we have our 2 reactants, we then want to figure out what the products are. So to figure out the products, we do our double replacement. The positive ions trade places. Calcium goes with carbonate, sodium goes with the chloride. So if the calcium goes with the carbonate, one product is going to be calcium carbonate, the other will be sodium chloride. Let's write the product for calcium carbonate first. Product's going to be CaCO3. And we get the CaCO3 because calcium is Ca with a charge of 2 plus, carbonate is CO3 with a charge of 2 minus. The charges are going to cancel each other out. The other product is going to be NaCl. NaCl, that's because the charge on sodium is 1 plus, the charge on chloride is 1 minus. Now the problem here is that we see a 2 down here and a 2 down here. How about we put in a 2 here and a 2 here? Is that the way we do it? No. How do we fix it? Right, we put a 2 in front of the NaCl in order to balance it. If you write them as subscripts, you are creating a formula of a substance that doesn't exist. Okay? You need to make sure that you are creating formulas only for things that do exist. And I would think most of you now, at this point, know that the formula of this stuff is NaCl. We call it sodium chloride. It's not Na2Cl2. It is NaCl. So now, this thing is balanced. It's not complete, though. We need some phase labels in here. So now to figure out the phase labels, that's what our solubility table is for. If we go back to our solubility table is broken into 2 parts. Those which are soluble are mostly soluble, and those which are mostly insoluble. If it's soluble, something that is soluble means it will dissolve. If it is insoluble, that means it will not dissolve. So now we need to figure out whether calcium carbonate dissolves or whether it does not dissolve. So we want a phase label for the calcium carbonate. So to do this, we need to figure out where calcium carbonate lies on here. And do you see anything where we see calcium or carbonate in here? At the bottom, we see carbonates under the category of mostly insoluble. We check to see if there are some exceptions for this. There are, but calcium carbonate is not one of the exceptions. So because it is insoluble, the phase label that would indicate insoluble is going to be S for solid. It's going to be S for solid. That means it doesn't dissolve. And for the sodium chloride, if we want to figure out its phase label, where do we find sodium chloride on here? At the very top. And this is one of the easiest to deal with. If it contains sodium, it's a compound that contains sodium, and it is mostly soluble, and there are actually no exceptions. So sodium compounds will always be soluble, and if it's soluble, the phase label we give is AQ. Exactly. AQ is the phase label for soluble, or means it dissolved. Insoluble, the phase label is S. Sometimes students will get it mixed up and think that S stands for soluble. S doesn't stand for soluble. S stands for solid. So now if we come back to this here and look at the demo we just did, remember we formed a white precipitate, and a precipitate is which phase? It's a solid. So we would now be able to identify what the white stuff is in here. The white stuff that's in here is which stuff? Go to our equation. What is the stuff that it is? Calcium carbonate, exactly. So we come back here, calcium carbonate is the solid, so the white precipitate that we formed in here is the calcium carbonate. And the sodium chloride is actually the liquid stuff that's going to be left behind. It's going to be the aqueous material that's left behind in the solution. And so again, we put in the phase label of AQ here for the sodium chloride to indicate that it's dissolved in water. Any questions on this one? Yes?
So would it always be aqueous or solid, never liquid or gas?
It could be liquid or gas. You know, this is an intro class, and I'd love to go through all those. If you really want to do those, then you can take our principles class with us, and we'll do the same stuff. We'll do in this class. We will see some, like the ones we have seen with the combustion and everything. We will, but I am not in here. I don't think expecting you to do gas products for these types of reactions. Okay. Anybody else? All right. Let's do another one. Let's look at these two substances, and let's write out some chemical formulas. We are going to mix together some, what is it? Iron 3 chloride. Iron 3 chloride and some sodium hydroxide. Iron 3 chloride and sodium hydroxide. Again, my suggestion to you would be to write the names one above the other. So again, iron 3 chloride. Remember that when we talk about the 3, it's a Roman numeral 3. Chloride. And then the other reactant here is going to be sodium hydroxide. We'll go ahead and put some iron 3 chloride into the one. And we'll pour out some sodium hydroxide into the other. And then we'll go ahead and mix these two together and see what happens when we do that. Pouring one with the other. Then we see the formation of a precipitate. We might describe this as being a brown or rust-colored precipitate. So now, in order to figure out what happened in this chemical equation, or this chemical reaction, we write out a chemical equation. We start by writing out formulas for the iron 3 chloride. Iron 3 means we have Fe with a charge of how much? 3 plus. Chloride is Cl with a charge of 1 minus. And again, we already looked this one up. We see that the chloride is a single minus. We didn't have to look up the iron 3 because the Roman numeral is what tells us that the charge here is a 3 plus. Sodium is Na with a charge of 1 plus. And hydroxide is going to be one of those we memorized. This is with a charge of 1 minus. Okay, so now we write out our reactants. Iron 3 chloride. Fe Cl3. Its starting phase here is aqueous. This is aqueous. Starting with an aqueous material. Then the sodium hydroxide would have a formula of NaOH. It's a single positive and a single negative. Their charges are going to cancel out. Again, its starting phase was aqueous. All right, then we want to try to figure out the products of this reaction. If we want to figure out the products of this reaction, we need to do our double displacement. So the positive ions are going to trade places. If they trade places, iron 3 will now pair up with hydroxide. Sodium will pair up with chloride. So now we write out the formulas for the products. We have iron 3 hydroxide. If we now combine these two together, formula is going to be Fe. Right, what do we need around this OH? Parentheses, because it's a polyatomic ion. Outside the parentheses, 3. And then our other product is going to be NaCl. That's because we have Na with a single positive charge combined with chloride, which is a single negative charge. Single positive, single negative charges will cancel out. Now we need to determine phase labels. If we determine phase labels, we need to look up iron 3 hydroxide. Iron 3 hydroxide we will find where? At the bottom, under the category mostly insoluble. We then check for exceptions. Is iron 3 hydroxide an exception? No, it is not. So, because it's not an exception, phase label here is going to be S. It is insoluble. It'll be a solid. Then sodium chloride. Where do we find sodium chloride? At the top. In this case, we could either actually look at sodium or chloride. They give us the same answer regardless of which one we look at. And that means because it's soluble, the phase label is AQ. We're not yet done. What else do we need to do to this one? Balance it. So to balance this, let's start by looking at the irons. How many irons here? How many here? 1. It's balanced. How many chlorines? How many chlorines? So what do we need to balance it? 3. Okay, at this point we look at sodiums. How many here? 1. How many here? 3. So what do we need? 3. Then we look at hydroxides. How many hydroxides here? 3. How many hydroxides here? 3. This then is your balanced chemical equation. So any questions on this one here? Okay, we have one more here. Let's look at this one. I have a couple substances. The two substances were... Oh, and by the way, you know what this rust-colored stuff is? It's rust. Yeah, it's rust. Okay? Or its chemical name is? Right, iron 3 hydroxide is its name. So that's actually wet rust. If you have dry rust would be iron 3 oxide. Wet rust is iron 3 hydroxide. Okay, so we'll move this on over here. Let's look at one more. Let's try potassium iodide and sodium carbonate. Potassium iodide and sodium carbonate. So again, we'll line them up here. Potassium iodide and sodium carbonate. And we'll put some of them in each of these beakers. And the potassium iodide looks like it's a little kind of yellowish color. It actually should be clear. It turns out there's a little bit of iodine or I2 in there, I guess. And it appears someone didn't wash this beaker. So we actually have two things that aren't looking the way they're supposed to look here. So this is looking pink. They should both be colorless, but we're still going to be able to get the right observation here at the end. We go ahead and mix these two together and watch what happens. It appears that nothing happened. Okay, so here's what we do in a case like this, and you should be able to predict this. Not yet, but we'll help you out as to how you would be able to predict it. First of all, if we look at the reactants, we have potassium iodide. Potassium is going to be K with the charge of 1 plus. Iodide is I with the charge of 1 minus. So it's going to be K with a positive, I with a single negative. And so that's going to be Ki. Its phase label is going to be aqueous. And if we look at sodium carbonate, sodium we've already looked up is Na with the charge of 1 plus. Carbonate is an ATE, which is one of our two memorized ones. CO3 with a charge of 2 minus. So if we wrote the chemical formula of sodium carbonate would be Na2CO3. Phase label of this would be aqueous. And when we write out the products of this reaction, we'd actually say that there is no reaction. And so we can't write out products if they don't react with each other. Then we can't write out products for that chemical equation. Now, here's how you could have predicted, though, whether or not this reaction occurred. And let's say that we weren't sure about it to begin with, so we did write out some products. Let's write out what those potential products could have been. So if we had done that, potassium would have paired up with carbonate, and sodium would have paired up with iodide. And had we done it, the products then would have been potassium carbonate, which would have been K2CO3. The other product would have been sodium iodide, which is NaI. If we had then gone from here to look at what the phase labels would be, we have potassium carbonate. So we go to our phase label. Do we see potassium or carbonate here? Well, we see potassium up here, but we happen to see carbonate down here. One is under the category mostly soluble, the other is under the category mostly insoluble. Well, let's see what we find out from this. Of course, if it contains potassium, it's soluble and there are no exceptions. So that should tell us right away we could label it as a phase label of AQ. But then you say, well, wait, what about the carbonate? So we look at carbonate. If you looked at this first, it's under mostly insoluble. But if you look at one of the exceptions, it is if it's paired with potassium. So either way, we wind up with the same result. The phase label of this is going to be AQ. And the phase label for the sodium iodide, well, because it contains sodium, its phase label is going to be AQ. Again, because it's soluble and there are no exceptions. So the rule goes something like this. If we start with two aqueous ionic compounds, and you might want to write this down if you can't remember it, or you can listen to it first and then write it down. If we start with two aqueous ionic compounds, and the products show that two aqueous ionic compounds would form, then we have no reaction that would take place. So if the reaction shows that we start with two aqueous ionic compounds, and the products show that two aqueous ionic compounds would be formed, then we have a case for no reaction. In fact, we can't write out products for this. We get rid of that right here, and we'd simply say that when we combine these two together, that there would be no reaction. And this is our conclusion.
So on the test, you wouldn't have to do the second step first because the first step is already showing that it's no reaction.
Correct, yes. Now, if you write no reaction and there is a reaction, then you're just going to get 0 credit, period. Okay, so if you want to be sure, you can show that these would have been the potential products and then show there's no reaction. But if you incorrectly label something as no reaction, there is one, then there's no ability to give partial credit on that. So, but if this is correct, and you write no reaction, then you can get full credit for this type of, yep. Anybody else? Okay, let's go ahead and practice these. So I'll write these out. We have lithium phosphate, Li3, PO4, aqueous. Combines with KOH, aqueous, to yield. Next one. We've got MgSO4, aqueous, plus CaBr2, aqueous, yields. And then we have this one, ammonium phosphate, aqueous, combines with barium chloride, aqueous. So for these three, here are your instructions. The instructions are to complete and balance these chemical equations. Complete and balance these chemical equations. However, I will tell you one of these three is in no reaction, only one of them. So the first thing I would do if I were you is to identify which one is no reaction, and then the other two will have reactions. Write out the products and then balance the equation. Again, one of these three is no reaction. For the remaining two that you find, complete and balance the equations. We're going to count down. 5, 4, 3, 2, 1. Correct answer is the very first one. The lithium phosphate to the potassium hydroxide is no reaction. You would get no reaction because if you had listed potential products, the potential products of this reaction would have been, whoa, need to get over here. They would have been lithium hydroxide, and they would have been potassium phosphate. They would have been these two right here, and the phase label for each one of them would have been aqueous. And what would have been a quick way to identify these as aqueous? This one contains lithium, so everything contains lithium is soluble, no exceptions. This one contains potassium, it is soluble with no exceptions. So you should be able to almost eyeball this one in advance and see if they trade places, and know that you wouldn't even have to worry about it because they contain lithium and potassium. Even trading places, they'd still be soluble. Yes, T?
Can you trade places with it first before you put anything in to balance everything else to see if they expect no reaction? Because that's what I do.
For sure. In fact, that's how I mentioned we should think about it. You should eyeball this one right away and say, oh yeah, everything with lithium is going to be soluble. See if it trades places, it's going to be soluble. This one contains potassium. Even if it trades places, it'll be soluble. So there'll be no options on this one other than to be.
And then I have another question.
Yes.
So once it reacts with after the arrow part, does it take the number with it, or does it just the number just
The No, the number does not come with it because remember that where those numbers come from is the charges.
Right. So once you write the new equation, then you have to balance it out from the start.
That is correct. 100%. Very good. Yep. Yep. And that's the struggle that many have is they carry those subscripts over. And so probably the biggest mistake I'd see on something like this one here is they would have carried over those subscripts and they would have written a formula instead of NaCl, would have written it as NaCl3. So, right. We do not want to carry those over. The way that we balance them is by putting in the coefficients. So very good. Okay, next up. I think this is Socrates app again. When this equation is completed and balanced with the smallest whole number of coefficients, a phase label of S is applied to which product? Phase label of S would have been applied to which product? So if we get our answers locked in here, please, we'll count down. 5, 4, 3, 2, 1. Correct answer there. Very good. Calcium sulfate. And that's because if you had put in your correct products of CaSO4 and the other product of MgBr2, phase labels here, let's see. Oh yeah, we're trying to decide. So one of the problems that students will have with the sulfates is they see the sulfate under the category mostly soluble. However, what else do we see over here? Right, we see calcium. So when it pairs up with calcium, it's going to be insoluble. If it's insoluble, the phase label is an S. This one here is AQ. Then if we look at the last one, when this equation is correctly completed and balanced with the smallest whole number coefficients, I don't know how this looks on the small screens. Who's got a small screen? Does yours all fit on one screen? Oh, yeah, okay. And it wraps around properly. That's good. A, B, C, or D? Or E, I guess. A, B, C, D, or E. Okay, we'll give you about 15 seconds here to get an answer locked in. And we'll count down. 5, 4, 3, 2, 1. Correct choice here is D. So on this one here, if you had gone through and correctly traded your ions, you would have come up with the products of barium phosphate and ammonium chloride. The barium phosphate would be a formula of Ba3, then in parentheses PO4 with a 2. Of course, that would have come from the fact that you would have looked up barium right here and seen its charge is 2+. Phosphate would be PO4 with a charge of 3-. And then for the ammonium chloride, ammonium, of course, is NH4 with a single positive charge. Chloride is single negative. Your products would have been NH4Cl. You then look up the solubilities. You'd see that phosphates are mostly insoluble, so we'd have an S. The ammonium chloride, because it contains ammonium, is soluble. Phase label is AQ. Then if you go through and balance it, oh, help me out here. First one would have been, is this a 2? The next would have been 3. This one would have been 1. And this one would have been 6. One of the questions that often comes up, how about if I had reversed these products? Let's say if I had written ammonium chloride plus barium sulfate, that would have been acceptable because, of course, I don't remember what this property is in mathematics. I think it's commutative. 3 plus 4 is the same as 4 plus 3. So the order of the products, if you had written the ammonium chloride first, followed it by the barium phosphate, that would have been okay. Any questions on these? Any questions? All right, looks like we got to kind of cruise through this last bit here of test stuff. If we look at types of reactions, these are the different types of reactions. We, of course, already went through combustion reactions, and we looked at double displacement. These are 2 of them that you need to know how to complete and balance. And so we've covered these already. But there are 3 other categories of reactions that we haven't covered, And for these three, you will only need to be able to identify the reaction type. You will not need to complete and balance. So again, only for these first two will you need to be able to complete and balance. The last three are single displacement, and then we'll skip down a bit. Next one here is going to be synthesis, which are also called combination reactions. And then the last category, number 5, is decomposition. So again, single displacement, synthesis, and decomposition. The three, you just need to know the types. You will not need to know how to complete and balance them. So for single displacement, here is an example. We could have A plus BC yields, or we could have A plus BC yields, and we'll have two different scenarios. Scenario 1 is this: if A is a metal. And the second scenario is going to be if A is a nonmetal. If A is a metal, what happens is that A and B trade places. A and B trade places. If A and B trade places, help me out now, the products we'd write would be B plus AC. And remember, because the properties are commutative, we could also write AC plus B. It'd be the same thing. What do you suppose A would trade places with if A is a nonmetal? A and C would trade places. Good. If these trade places, then the products would be C plus BA. Good. A synthesis reaction or combination reaction is just like what it sounds like. We have two reactants coming together to form a single product. And a decomposition reaction, we start with a single reactant, which we can call AB, breaking down to be A plus B. So a synthesis, or combination, means we combine together two or more reactants into a single product. Decomposition means we start with a single reactant, we wind up with two or more products. We have 3 examples here left on your Socrative app. Let's see if you can identify these 3. You're going to classify them now. This was a day 1 reaction we looked at in here, and then we revisited it last week. This was the exploding hydrogen balloon. We reacted hydrogen with oxygen to produce H2O. Look now at the 4 types or 5 types. There's actually 2 answers to this one. Two answers to this one. We count down now. 5, 4, 3, 2, 1. It is a synthesis because we have 2 reactants and 1 product. It is also combustion because we are reacting hydrogen in the presence of oxygen. So if we burn something in the presence of oxygen or react in the presence of oxygen, that's going to be a combustion reaction. Good. Next one. This is the one where we took and made the genie in the bottle. We decomposed the hydrogen peroxide to make water and oxygen gas. By the way, the catalyst we saw for this the other day was manganese 4 oxide, but another catalyst for this reaction is blood. If you ever put hydrogen peroxide on a cut or wound, it bubbles. We see this reaction. I know I already gave away the answer. It is decomposition. Here's the last one. And this is the one I was going to demonstrate, but somehow we ran short of time, so I'm going to try to remember to demonstrate this. Let's see, today's Thursday, so I'll demonstrate this next Thursday after your exam. Copper reacts with silver nitrate to form copper 2 nitrate and silver metal. Get your answers locked in, please. We'll count down. 5, 4, 3, 2, 1. Single displacement. Any questions? All right. We'll see you later. Test on Tuesday.